It's time for us to practice using intervals. So on the top here, we've got 3 different intervals. Each one is represented in a different way. One is using interval notation, the other is using a graphical real number line, and the third one is using set builder notation. The challenge is to take each of these 3 different intervals and represent them using the 2 other ways. Then on the side, we have 4 other intervals, and these are defined by either the union or the intersection of 2 intervals. So try and put these 2 intervals together, either union or intersection, and describe what the new interval will be. Try and do it using interval notation, set builder notation, and also graphically on a real number line. So why don't you pause the video here and give it a shot, come back, and we'll do it together. All right, so let's give it a shot now. Let's look at the first one. We have an interval from 1 to 5. Okay, what is this going to look like? Well, let's describe this using set builder notation first. So this is going to be equal to the set of all x, such that 1 is less than or equal to x is less than 5. And there we go. That is the same interval in set builder notation. Now, if we were to describe this using a number line, let's see, we could describe this. Let's put down a point here for the number 1, and then it's going to go out to the number 5, and then we're going to have to fill in everything here between it. Okay, so there we go. This is going to be the graphical representation of this interval going from 1 to 5. Hopefully you got that one. Let's try the next. Okay, so for this one, we have it already represented graphically. So let's translate this to so we'll do interval notation first. Okay, so this is a closed interval. So we should have it going from -2 to 1, closed interval. And using set builder notation, it's going to be the set of all x, such that -2 is less than or equal to x is less than or equal to 1. And there we go. Okay, not too bad. Let's try the next one. This one is written in set builder notation. Let's translate this to interval notation first. Okay, so this is the set of all x such that x is less than or equal to -1. So this one is actually going to go all the way to -infinity and then up to -1, and that's going to be a closed boundary on the -1 there. Representing this using a real number line, we should expect to get something, well, we just need to mark down the -1. Okay, so let's say that this is the origin, and I have my -1 here, so I'm going to have this as a closed boundary, and then it's going to go all the way to -infinity, something like that. Okay, so hopefully this is what you got for the 3 intervals, translating them into the other 2 forms. Let's take a look at those union and intersection problems. Okay, so for these, what I'm going to do first is I'm going to translate both of these intervals into a graphical representation. That'll let us see what's going on. Okay, so for the very first one, we're going to have essentially an interval here. Okay, so we're going to go, let's say we go from 2, this is open here, open at 2 to 5, which is also open. Okay, so we're going to fill that in there. There we go. And then we're also going to have another interval over here, and this one is going to go from 3, and it's closed at 3. And it's going to go up to 10, where it's also closed. And so this is going to represent what we have here. So we're going from 3 to 10. And now we need to do a union operator here. So we're going to get the union of these 2 intervals. So that's going to be all of the points that are in the first interval or also in the second interval, right? So this is the logical OR operator. So we're going to start here with 2 and we're going to go up to 10 inclusive. And this represents then all of the points that are in either the first or the second interval. So let's take this. This is our representation then of the new set, the union of those two sets there, and let's write this using interval notation. So we're going to have an open interval from 2 to 10, and that is going to be a closed boundary there. And then we just need to write this in set builder notation. So this is the set of all x such that 2 is less than x is less than or equal to 10. Okay, there we go. That's the first one. Let's try the next one. There we go. Okay, so we now have an intersection of these two intervals. So we want to think about what that's going to look like. That's basically where they overlap, the points that are in the first interval and also in the second interval. So we can see we're going to have point 3 here, and that's going to go up to point 5, but not including it because it's not included in the first one. And so then we can just fill in everything right there. Okay, so this is going to represent the intersection of those two intervals. Let's write this in interval notation form. So this is a closed boundary here from 3 to 5. That's an open boundary. And in set builder notation, that'll be all x such that 3 is less than or equal to x is less than 5. Okay, so there we go. That's the set we get from the intersection of those two sets. Let's look at the next one. So here we have the union of these two sets. Let's try and represent them graphically first. So on the real number line, the first one is going from -infinity to -1. Okay, so let me just mark out the origin here, and here is -1. So this is going to be a closed boundary on -1, and then we're going to go all the way to -infinity, something like that. Okay, so this is going to represent my, my first interval. And let's grab a copy here and let's take a look at the second interval. So once again, I'll mark my origin. Here we're going from 1 to 3. Okay, so let's mark that down. We're going to go from 1, that's a closed boundary, up to 3 with an open boundary. So it should be something like that. Okay, perfect. And then we want to finally get the union of these two intervals. And, well, there's no overlap, so they're just going to sort of stay the way they are, right? So let me mark that down. We're going to have the origin. We'll have a point 1 going to point 3 open, and then we'll have a point here -1. And so let's fill everything in here. So that's going to be the interval on that section, and then also on this part going all the way to -infinity. So this will represent the union of these two intervals. Let's put that over here and try and represent this using interval notation. Well, there's no way to do it other than just write it exactly like that. Like there's no shorter, more concise way of doing it, and so I'm just going to write it exactly the same way. It's going to be the interval from -infinity to -1 closed, union with the closed boundary on 1 to 3 open. That's it. Okay, that is how we represent this in interval notation. And in set builder notation, this will be the set of all x such that -infinity is less than x is less than or equal to -1, or 1 is less than or equal to x is less than 3. And there we go. That will be the set builder notation here. Let's try the next one. Before we do that, let me copy these two graphics here. And we'll paste them over here. And so now we can try and evaluate what the intersection of these two intervals will be. And if you look at this, the intersection is the overlap, right? Those are going to be the points that are in the first interval and also in the second interval, But there is no overlap, right? There's no points here and there's no points here. So what we're actually going to get is just an empty number line, right? This empty number line is the intersection of these two intervals. And so we can also, if we wanted to, represent this as either the empty set or the empty set, right? So there's no other interval notation that we can use here because there's nothing, right? There is no interval. It is an empty set. Okay, so hopefully this was a good practice here using intervals in both interval notation, set builder notation, graphically on the real number line, and understanding how we can get the union and intersection of these to create a new set or a new interval.